So, I'm going to spend a little bit of time talking about the lab right quick. Then we're going to go out to the solar array. I got to do this kind of live thing. It's just kind of cool to see the process. Then we'll come back in here. We'll work on the lab. We'll talk some more about the lab. Then I've got to go back out there for another segment at 8:30, and you guys are just going to stay in here because you would have seen the process. Not a big deal. Lots going to happen there. And then Mr. Woodruff's going to come in here and watch you guys do that. Then as soon as I get done with that, then I'm going to come back in here, and then he's going to leave. And that's kind of the plan for the day. So it's going to be a little bit of, as best I can figure out, controlled chaos. So let's go with it. All right. So in terms of the lab, so let me clarify what I want. So down here, did you start that?
Yeah.
Okay. So down here on the bottom, when I say show the calculations for trial number 1 in the space below, when I say show calculations, I don't want the formula, okay, in terms of just the formula. I don't sit there and go, oh, period is, or if you want to find, for example, the velocity, find the period of one revolution in circumference. If you just write 2 pi r, that is not showing me the work, okay? You need to write that down, but then you also need to say, hey, what are the numbers? I only want these calculations for trial 1. I don't want to see all 12 sets of calculations, okay? But I want to see one complete set of calculations for trial 1. The weight of the hanging mass, not the mass. Do not put down, 0.1 kilograms, okay? Weight, remember, is a measure of gravitational force. So here's this rubber stopper. It's swinging around. And again, here is the key assumption that we are initially going to make. The key assumption that we're going to make is the weight of what's ever hanging down, which in this case in trial 1 would be 0.98 newtons, is what's creating the centripetal force, okay? Because that centripetal force has to act inward, and that's what gravity is doing. It's pulling and providing that inward force to keep that rubber stopper moving around in a circle. Okay, so on trials 1 through 4, keep in mind what you're changing. Trials 1 through 4, you're going to look at mv squared over r, okay? Trials 1 through 4, you were creating more and more centripetal force because you were carrying more and more weight from the bottom. The mass of the stopper and the radius is a fixed value. That's not going to change in 1 through 4. So the only way that you can create a bigger centripetal force is if you have a bigger and bigger velocity. That's the only way it's going to work. Now, when you get to 5 through 8, now you're going to change the dynamic. Now you're going to keep the centripetal force the same, maybe use the 0.2 kilogram, 0.3, whichever group here decides, but you're going to keep that as a constant. You're going to keep the mass of the stopper a constant. Then you're going to change the radius. Oh, okay, maybe you start with 0.5, 0.65, whatever, okay, but have at least 10 to 15 centimeters of change when you're altering the radius. Okay, then on the last ones, then you're going to change the stopper itself. So that's going to be mv squared over r. So now, this is the only one that's going to be an inverse relationship. So if you're going to keep the centripetal force constant, if you increase the mass with the same radius, your velocity has to decrease. So when you're answering these questions, 4, 8, and 12, on 4, 8, and 12, you make sure that you have mentioned all 4 of these variables: centripetal force, mass of the stopper, radius, and velocity, okay? And you're going to say, hey, these 2 values changed and the other 2 were constant, and because of that, this is what happened, okay? So you're going to take a sheet of graph paper, you're going to draw 3 different graphs. 2 of the graphs, I explicitly tell you, are going to start at 0, 0, okay? So the first 2 graphs you're going to draw are going to start at 0, 0. One's going to look like this, the other one should kind of look like that, and your third graph should look something like this. So the first 2 graphs, you start at 0, 0. The third graph, that's going to be that inverse relationship one. Okay, so let's pack up, shut that down. We'll go outside. We're just going to chill out. I'll do the interview. And
It's hard work being famous.
Okay, so I'm going to get back out there in about 10 minutes. So here, let me take you through what's going to happen on number 13, okay? So number 13, we're going to see if the actual data matches up with the idea that the centripetal force created by the hanging mass is actually equal to the centripetal force calculated a different way. So on trial number 4, you had a 0.4 kilogram mass hanging down, which was, I think, 3.92 newtons, if I remember right. So that's our theoretical value for our centripetal force. So now we're going to see if your data matches up with that and how close that is. So, and you're only going to do this in trials 4, 8, and 12. So you're going to go to trial number 4. You're going to take the weight of whatever was hanging down, which in this case is going to be 3.92 newtons. Okay? That's our theoretical value. Now, we're going to calculate centripetal force using mv squared over r. Okay? So now, you're going to go to trial number 4, and you're going to take the mass of your stopper, make sure you've converted from that grams into kilograms, divide by 1,000, not by 100, divide by 1,000. Okay? So that's going to be the mass of your stopper. You're going to have your velocity, okay, because you did 2 pi r over t. You took the circumference and you divided by the time for one revolution. So then you're going to have your velocity, and your radius is going to be 0.8 meters, okay? So you know everything. So you're going to calculate centripetal force using mv squared over r. So then we're going to look at how close these values are. So remember, experimental error is your theoretical minus your experimental divided by your theoretical times 100. So you're going to take that 3.92 newtons, which is the weight of what's ever hanging down, minus what you get from mv squared over r, divided by 3.92 times 100, and remember that's an absolute value, okay? So what you're going to have those two lines. One is that calculated centripetal force, that's from mv squared over r. Your experimental error is going to be the difference between those values multiplied by 100. It's an absolute value thing. Okay, got it? Good? Grand. So we will talk about, I got to get back out there. If you can get through that today, that's going to be cool. We'll finish the rest of this lab in terms of the calculations and everything tomorrow. So today, focus on getting the data. I'm going to head back out. I'm going to have Mr. Woodruff come over and be in the room. So, we're good?